everyone. In this session, we shall move on to the next chapter, which is three-phase induction motor, which comes under 5th module. In the previous session, we have discussed about the synchronous generator. So, that is the first chapter in the 5th module, and the three-phase induction motor is the second chapter in the 5th module. Okay. And so, here in the previous session, we have discussed about the synchronous generator, and we also call it as AC generator. Right. And in this session, so we are going to discuss about three-phase induction motor. Now already I hope you are already familiar with the difference between the motor and the generator. Right. And here the generator is a machine or the device which converts mechanical power to electrical power is nothing but a generator, and similarly motor is nothing but it is a machine which converts electrical power to mechanical power is nothing but a motor. Right. Okay. So, here we have a three-phase induction motor. Three-phase induction motor means which gets the supply. So, what type of supply it is? It is three-phase supply. So, three-phase induction motor is an AC motor. So, remember three-phase induction motor is an AC motor. Synchronous generator can also be called as AC generator, but three-phase induction motor is an AC motor. Here the machine which gets the supply. So, three-phase supply and produces the mechanical power. Remember, it is a machine which gets the supply, that is three-phase supply, and which produces mechanical power. And out of all AC motors, three-phase induction motor is extensively used because of these reasons. So, the reasons are here the construction, its construction is simple and rugged. Okay. So, three-phase induction motor, the construction is simple and rugged. So, rugged means it is almost unbreakable, and similarly it has good speed regulation. So, these are some of the reasons that why the three-phase induction motor is extensively used. And next is efficiency is high and cost is low. Next, induction motor. So, wherever I mention IM, it is indicating that induction motor. Induction motor are self-starting. So, it has self-starter. Hence, motor of small rating do not require a starter. So, remember, since it has a self-starting or the self-starter, so especially for that is motor of small rating do not require any starter. And next is the starting arrangement for larger motors are simple. So, as I have already indicated, so these are the reasons that why we prefer or why three-phase induction motor is extensively used out of all AC motors. So, next we will move on to the concept of three-phase windings. So, now before we move on to the constructional details of the three-phase induction motor and the working principle of three-phase induction motor, so you need to understand the concept of the rotating magnetic field. So, this you might have already observed in three-phase circuits, the same waveform and this vector diagram. So, already you have learnt in three-phase circuits. The same concept we are going to repeat here, but in this case, so we are talking about a concept of rotating magnetic field. Okay, concept of rotating magnetic field. And as you can see here, okay, so this is these are the three windings. These are the three windings where it is placed with 120° apart, and these three windings are connected to. So, the other end or the initial end or the starting point of these three windings are given to three-phase supply. Okay, so that you can just observe. So, this A point is given to R and B point is given to, or B winding is given to this Y, and similarly here the C point is given to B. Okay. So, this picture depicts the rotating, like how these three windings can be connected to three-phase supply. And of course, so when the supply is provided here, so when three-phase supply is provided to three windings in a stator, three windings in a stator, so we can have a rotating magnetic field with a constant magnitude, and rotating with the speed of, that is rotating in synchronous speed, that is ns. So, remember, when three-phase supply is provided to three windings. Okay, so 3 windings. Then what happens here? So when of course when the current passes through it, so we can have a rotating magnetic field, right? So we can have a rotating magnetic field or the magnetic flux. So with the constant magnitude, so that you can just observe in this figure. So we have a constant magnitude over here, and so with the speed of ns. So ns we call it as synchronous speed, that is in the stator. So remember, so the concept what we have considered here, that is rotating magnetic field. So this comes under the stator part of the motor. So this comes under the stator part of the motor. So this is how the construction is made at the stator. And so you can see here the flux, 3 different flux which we have obtained from 3 different windings. So that is from A. So from A, so we have the flux, and of course this is the maximum flux phi m, right? And how do we represent it in equation? So what is this phi A? So phi A is equal to, so what is phi A? So this we call it as phi A, and this is phi B. Next is phi C. So what is phi A? So phi A is equal to, which is phi m sin omega t. As we have already discussed the same concept in the 3-phase circuits, so we are going to represent this as, but in 3-phase circuits, so we have represented in the form of voltage, that is induced EMF, but here since we are talking in terms of the rotating magnetic field, here we represent it in flux, that is phi. So phi A is equal to phi m sin omega t. Similarly phi B is equal to, so what is phi B? That is the next waveform, so that we can represent it as phi m sin omega t minus 120, because there is a delay between the first waveform with the next waveform. So there is a delay of 120 degrees, so which can be considered as omega t minus 120. And similarly, so what is phi C? Phi C is equal to phi m sin omega t minus 240. So which is phi C. So you look at this waveform. So there is a delay between the 0 to, that is the first waveform to the last waveform is 240. So this can be written as phi C is equal to phi m sin omega t minus 240, and phi C can also be written as phi m sin omega t plus 120. Okay. So this can be minus 240 can be written as plus 120. So these 3 can be represented, that is in form of vector. So that is in the form of vector. So this can be represented as phi A, this is phi A, phi B, of course we have 120 degree difference between phi A and phi B, and similarly so we have 120 degree difference between phi C and phi B. So that you can observe here. And so what is the angle difference between phi A and phi C, which is of, if we move on to this direction, which is 240, or in this direction it is 120. So that is why phi C equation can be considered as phi m sin omega t minus 240, or else phi m sin omega t plus 120. So this is the concept of rotating magnetic field. Now you can see the construction of the induction motor. So let's look into the constructional details of the induction motor and working principle of the induction motor. As we have already discussed in the previous session, that is in the synchronous generator. So we have 2 different parts. One is the stator part and another one is the rotor part, and the stator is always stationary part and rotor is the rotating part. Similarly, you can also observe the same in this figure. So outermost layer, so which protects, or outermost layer of the motor is nothing but the stator, and which is always a stationary part, right? And the stator core is always made up of, or it is made with high grade silicon steel, and here a large number of axial slots are cut into, that is inner periphery, around the inner periphery of the stator core. So you can just observe, as I have already indicated, so this is the stator part, and you can see here this is the stator frame, right? And so you can see when we consider the construction details, so you can see this is the stator slot, so where we can accommodate the stator 3 windings or the conductors, the circles or nothing but the stator 3 windings, and so this is nothing but stator slots where we can accommodate the windings. So as I have already indicated, so the stator is made up of high grade silicon steel with high permeability to reduce hysteresis loss, and as I have already indicated, a large number of axial slots are cut, okay, around the inner periphery. You can see here around the inner periphery, right. So these are cut around the inner periphery to accommodate the 3 windings or to accommodate the conductors. And similarly, so if we look into the rotor part, so in this rotor, of course the rotor is the rotating part, and rotor is mounted on the shaft. The rotor is mounted on the shaft, so where the load can be connected. As you see here, so this is nothing but Ns is nothing but the rotating magnetic field with speed Ns. Okay, so with Ns, this we call it as synchronous speed, and F is the frequency. As I have already explained in the concept of rotating magnetic field, so we have a speed called Ns, that is synchronous speed, and the frequency is F. And similarly, so the rotor speed, which is indicating as N, that is a rotation of rotor with speed N, and the frequency is F dash. So remember here the rotating magnetic field, so the speed of the rotating magnetic field is Ns, that is synchronous speed, and the frequency is F, and here you can see it is the speed of the rotor, that is rotation of rotor with speed N with the frequency F dash. And of course this is stator 3 windings, and the shaft to which mechanical load can be connected. So load is connected, and of course this whole rotor is placed on the cast iron frame, right. And this is the rotor slots. So these are the rotor slots, so where we can accommodate the conductors. And of course, and so till now we have discussed about the constructional details of the 3-phase induction motor. And when we come to the working principle or principal operation, working principle, 3-phase supply, initially 3-phase supply is given to the winding, so 3 windings. Of course, when it is given to 3 windings, so we can have a rotating magnetic field with a constant magnitude, and with the speed Ns. So we can have rotating magnetic field, so around this stator core. So that is nothing but Ns, that is the speed of Ns, synchronous speed, and with the frequency F. This rotating magnetic field, so later the rotating magnetic field links to the conductor. So when it links to the conductor, there will be an EMF, that means EMF will be induced. So when the rotating magnetic field links to the conductors which are placed at the rotor, EMF will be induced. So later the induced EMF sets up a current in the rotor in such a direction that, so to produce the torque, here to produce the torque, look at the direction in the same direction. So same direction of the rotating magnetic field. So and what happens here, of course, which makes the rotor to rotate. So this is nothing but the working principle of the induction motor. And later, so here you know what is Ns, it is the speed of the rotating magnetic field, and N is the speed of the rotor, okay. So speed of the rotor, and here the relative speed of the rotor decreases. Initially of course it decreases, and gradually it increases. Gradually the speed of the rotor increases, but here it tries to catch up the speed of Ns. Right. So later of course when it increases, when N increases, initially so it decreases, and like gradually it increases, and when it tries to catch up the speed of Ns, so what happens when it tries to catch up the speed of Ns, then the relative speed means Ns minus N becomes 0. Okay, Ns minus N becomes 0. When both the speeds are same, that means Ns is equal to N. When both the speeds are same, so as I have already indicated, so it tries to catch up the speed of Ns. So once it becomes equal, so when these two are equal, then the relative speed becomes 0. The relative speed means the difference between Ns and N. when the relative speed. So what is relative speed? The difference between this ns and n. When the relative speed is equal to 0 or it becomes 0, that means to say the speed of the rotor is equal to the synchronous speed. So when ns minus n is equal to 0 or ns is equal to n. So when both the speeds are same here, so there so no change in flux. So when there is no change in flux, then so no EMF. So of course when there is no EMF, so there will not be any torque produced. So remember, so because of this reason, that is when ns is equal to n or when n is equal to ns, finally so there will not be any torque produced in the machine. So next, based on this ns and n. So ns is the synchronous speed, that is the speed of the rotating magnetic field, and n is the speed of the rotor. So based on these two parameters, so we are going to define two equations here or two terms. So one we call it as slip speed. So what is a slip speed? Slip speed is the difference between, so the speed of the rotating magnetic field, so which we call it as synchronous speed, and the speed of the rotor. So the difference between ns and n is nothing but, or ns minus n is nothing but slip speed. And similarly, so we have another term called slip, and we denote this as S, of course in terms of percentage. The slip is defined as the ratio of, the slip speed to this synchronous speed. Okay, ns minus n is the slip speed and ns is the synchronous speed. So this is nothing but slip. And so next we have the significance of slip. So what is the significance here? So what is the significance of slip? So that is finding out the slip. So remember, as I have already explained like just now, this significance of slip, that is in actual practice. So that is practically in actual practice. Here the speed of the rotor or the rotor should not run at the speed of the rotating magnetic field. Okay, I will just repeat, in actual practice the rotor should not run at the speed of the rotating magnetic field. So that means to say the n should not be equal to ns. Okay, in actual practice the speed of the rotor should not run at the speed of rotating magnetic field. Okay, but so if it does so, that means when n is equal to ns, if it does so, that means n is equal to ns, then what happens? So here this becomes 0. So slip speed becomes 0. So ns minus n is equal to 0. Of course, when ns minus n is equal to 0, so remember, so no relative movement between the rotor and the rotating magnetic field. Right. So when ns is equal to n or ns minus n is equal to 0, so you can have, that is, or no relative movement between the rotor and the rotating magnetic field. So when there is no relative movement, then so what happens when there is, like, of course there will not be any change in flux, isn't it? So no change in flux, and of course when there is no change in flux, then so EMF will not be induced. So remember, when there is no change in flux, so EMF will not be induced. So no induced EMF. So finally, when there is no EMF, so no torque to drive the motor. So there will not be any torque produced, that is to drive the motor. So this is the significance of slip, which is very, very important. Now, so let us derive the expression of rotor speed in terms of the slip and the synchronous speed. So as you have already learned that S is equal to, which is the ratio of, what is S? S is nothing but the slip, and which is the ratio of relative or the slip speed ns minus n, so to this ns. Right. Now I want to get this n. So how do we get n? Which is equal to, that is S into ns is equal to ns minus n. And if you want to get only n is equal to, so I have taken n other side, and so just simplify this, this becomes ns minus s into ns. So n becomes, take ns common, this becomes 1 minus s. Okay. So now here we have tried to express, so here, so we have tried to express the rotor speed in terms of the synchronous speed, and that is in terms of slip. So n is equal to ns into 1 minus s. And similarly, so we have to find out the frequency of the rotor current. Okay, frequency of the rotor current. So we have just defined the rotor speed n, and the frequency of the rotor current is denoted as f dash. So remember ns and n, f, so which are related to the rotating magnetic field, and similarly so n and f dash. So these two are the parameters, so which we define, which we consider for the rotor. So ns and f, synchronous speed ns and f are the parameters so that we define it at, that is at the rotating magnetic field, and similarly n and f dash are the two parameters which we define at the rotor. And the frequency of the rotor current, so it is f dash. So how do we get this f dash? And remember f dash is equal to, and as we have already learned that f can be expressed as np divided by 120. Okay, so this is the general expression of frequency, so related to the speed and the number of poles. Similarly, here we express f dash as since the frequency of the rotor current depends on the relative speed, that is the slip speed. So this we can consider it as ns minus n into p divided by 120. Since the frequency of the rotor current depends on the speed of the rotating magnetic field, or so depends on the slip speed, so we define f dash as ns minus n into p. So instead of having only one speed, so we are going to have the slip speed, so ns minus n into p divided by 120. And similarly, so we have another frequency. So remember this f dash is nothing but the frequency of the rotor current. And similarly we have another frequency that is f. So what is this f? F is nothing but the frequency of the alternator. So remember, so f is the frequency which is related to the rotating magnetic field. Okay. So now since this depends on only ns, since this f depends only on the synchronous speed, f can be considered as ns into p divided by 120, and f dash is ns minus n into p divided by 120. So now we have got two equations. So one is f dash and another one is f. Okay. So let us call this equation as 1 and this as 2. But remember f dash is nothing but the frequency of the rotor current. Now based on f and f dash, so we are going to find the relationship between f dash and slip. Okay. So this is very, very important. We are going to have, or we are going to derive the expression that is to provide the relationship between f dash and slip. So what is S here? So let us find the relationship between S, f and f dash. So what is S? S is nothing but slip. So slip is ns minus n divided by ns. Okay. So let's call this equation as 3. And okay. So can we get only ns from this equation? Of course, ns is equal to 120 f divided by p. Okay. So which we have obtained from equation 2. Let us call this equation as 4. So we have obtained only ns from equation 2. So let us call this equation as 4. And similarly, so can we get ns minus n from equation 1? Of course, ns minus n can be considered as 120 f dash divided by p. Let us call this equation as 5. So now we have obtained ns minus n from equation 1, and let us call this equation as 5. Now substitute equation 4 and 5 in equation 3. So substitute equation 4 and 5 in equation 3. So we get s is equal to what is ns minus n, which is 120 f dash divided by p, and what is ns, which is 120 f divided by p. So pp gets cancelled, right? And of course 120. So finally what is S? S is equal to f dash divided by f. So now we have obtained the equation which provides the relationship between the slip and so two more parameters are here, f dash. So what is f dash? F dash is the frequency of the rotor current and f is the frequency of the rotating magnetic field. So finally S is equal to f dash divided by f. So these all about like slip speed and the frequency of the rotor current, then frequency of the rotating magnetic field. Thank you.